My dear students, today we will discuss about double refraction. This is a phenomenon of light transmission through anisotropic minerals or the minerals which crystallize in non-cubic systems. The minerals which crystallize in cubic system allow the single light rays to be refracted as single light rays. So there we cannot say that double refraction is taking place. Similar is the case with the amorphous substances. There, from a single incident ray, we get one refracted ray. But this case is totally different in case of anisotropic substances. In anisotropic substances, from a single light wave, we get two refracted waves within the mineral. These two waves have two separate wavefronts having two separate velocities. The mineral has therefore two different indices corresponding to the single incident ray. So, the mineral shows two different indices for the two light waves, and this phenomenon is called double refraction. Or we can define in other way, the phenomenon of getting two refracted rays from one incident ray is called double refraction. And this is a case with all anisotropic substances. In anisotropic minerals, light waves travel with different velocities in different directions. In case of minerals which crystallize in tetragonal, hexagonal and trigonal crystal systems, there is one direction which is parallel to C crystallographic axis direction, along which if light wave is propagating, it will not be doubly refracted. So, the minerals which crystallize in tetragonal, hexagonal and trigonal divisions or hexagonal systems, we see that there is one direction along which if light is being propagated, there it suffers no double refraction. That's why this C axis along which there occurs no double refraction is designated as the optic axis. So, because there is one optic axis, that's why the minerals which crystallize in tetragonal and hexagonal systems are said to be uniaxial crystals. And they have one optic axis direction along which if light is being propagated, it will suffer no double refraction. But in case of minerals which crystallize in orthorhombic, monoclinic and triclinic crystal systems, there we find two directions along which there occurs no double refraction. And these directions do not match with any one of the crystallographic axis direction of the crystals. But in case of uniaxial, the C crystallographic axis direction was matching with the optic axis direction. But in case of biaxial minerals, we do not find the optic axis direction to match with any one of the crystallographic directions of the minerals. As we see that there are two optic axes. In case of a biaxial mineral, we find two optic axes. Along which, if light is propagating, it will suffer no double refraction. It will not suffer no double refraction. As they possess two optic axes, that's why they are said to be biaxial. So, crystals of orthorhombic, monoclinic and triclinic systems are said to be biaxial. Thus, we can classify the entire crystal kingdom into three types. They are isoaxial, uniaxial and biaxial. Isoaxial is the crystals which crystallize in cubic systems. Uniaxial, in case of uniaxial, there is only one optic axis and it is the case with tetragonal and hexagonal systems. If it is biaxial, it is the case with orthorhombic, monoclinic and triclinic systems. And these uniaxial or biaxial crystals, they display the phenomenon of double refraction. And there is no double refraction along the optic axis direction. So we can define optic axis as the direction along which there occurs no double refraction, or it is the direction of zero birefringence. Birefringence is the difference between the two refractive indices corresponding to the O ray and E ray, or we can say fast ray and slow ray, because these two rays, they do not move with same velocity. One moves with a faster velocity, the other with a slower velocity. They can be simply designated as fast ray, slow ray, or in case of uniaxial minerals, they are designated as O ray and E ray. Thus we could know what is optic axis, what happens when light is propagated along that direction, and so we see that when it is a uniaxial crystal along which light is being propagated, it will be split up into two rays. One is ordinary, the other is extraordinary ray. And these two rays, they vibrate in two mutually perpendicular planes. They are found to be totally polarized and they vibrate in two mutually perpendicular planes. The ordinary ray obeys the rules of refraction, because when the light is incident normally, it will get refracted in that direction and we will get another ray which will deviate from this normal incidence. So, if it is as per the rules of refraction, the light incident normally to the surface will pass straight through the second medium with a change in velocity, but there should not be a change in the path. But here, in case of anisotropic substance, from a single wave we get two waves, one obeys the rules, one does not obey. That's why this is the ray that obeys the rules, that is called O ray or ordinary ray. The ray that does not obey, it is called extraordinary ray, E ray. So these are the two rays which are being produced from a single incident ray. One is ordinary ray, other is extraordinary ray, or one can be said as slow ray, the other is fast ray. But in case of uniaxial crystals, the O ray wave moves with equal velocity in all directions. That we have to remember. The wavefront of O ray is a circle, but E ray has a velocity which differs from direction to direction within a crystal. That's why the wave surface of the E ray is a ellipsoid, or this wavefront will be an ellipse. But as we know that C-axis direction is the direction along which there occurs no double refraction. So O and E, they have same velocity along the C-axis direction. That's why the circle and the ellipse, they match along the C-axis direction. In fact, that a single incident wave of light is split up into two rays that can be best studied by using transparent calcite crystal. Or we know that transparent calcite is the Iceland spar. This can be best used to study the phenomenon of double refraction. For that purpose, we place a piece of paper and over it we mark a dot mark through our ink pen, and if we place the transparent calcite over it, immediately above it there will be two images. One directly above the subject, other a little distance away. And if this calcite piece is rotated, this image will be fixed and this will rotate. And the image which is directly produced by the subject is due to ordinary ray. And this one which is rotating, this is due to E ray. Thus, it is concluded that the O ray obeys the rules of refraction, E ray does not obey because it is a normal incidence of the light. From there we say light ray has been deviated through refraction, so it is not obeying the rules of refraction. That's why it is in E ray. And O ray velocity is found to be constant throughout the mineral. And here, why the O ray velocity is found to be constant and not that of the E ray, that we have to discuss. So this is the figure that we see. Here the light is moving parallel to C-axis. It is not found to double refracted. So C-axis direction is that direction where we do not find double refraction. But here, C-axis, this is C-axis direction. Light is incident at an angle to the C-axis. So we are getting two rays. One is ordinary, the other is extraordinary. Both are found to be polarized, completely polarized. And these two rays that we see here, they are found to be polarized in two planes and their vibration directions are mutually perpendicular. If one is vibrating like this, the other will be vibrating like this. So that this ray and this ray, they will be mutually perpendicular. The direction of vibration will be mutually perpendicular. So the ordinary ray obeys the rules of refraction, and it is always found to vibrate in the basal plane of the uniaxial minerals, because of which its velocity is constant. But E ray vibrates in a plane that contains the incident ray and the of the axis. That we have to remember. As the atomic structure in the basal plane is uniform and O ray vibrates in that basal plane, its velocity is found to be same throughout the mineral. Whereas the E ray that vibrates in a plane that contains the incident ray and the C axis, because of which it is found to have different velocity in different directions. Let us see this diagram that will clearly define how the double refraction takes place in minerals. Let us imagine this is a tetragonal crystal. If light is incident in this manner parallel to this place, it is hitting perpendicular to C axis, moving parallel to C axis. In that case, it is the case with basal plane. Light is vibrating in the basal plane. As I discussed earlier, this is the plane where the atomic structure is uniform. So, and this is the basal plane. This is the plane for O ray, where O ray vibrates. O ray velocity is found to be constant because of its vibration in this plane only. But in this plane, if you take into account the E ray will have the same velocity as that of the O ray. That's why we do not describe the C axis direction to be the doubly refracting direction, or it is the optic axis direction along which there occurs no double refraction. If light is incident in any other plane, let us say this is the plane. This is the plane. If light is incident on this plane, the C axis is here in this direction. This is the C axis direction. This is the incident ray. So the plane which contains the incident ray and the C axis, this is the plane. So in this plane, the C axis will have to vibrate. So here we will also get the O ray. O ray always vibrates in the basal plane. So basal plane is like this. Is this a basal plane? So O ray will vibrate like this. E ray will vibrate like this, because the vibration action of O ray and that of the E ray are mutually perpendicular. Thus, we can conclude that any ray of light that enters into any unstable substance is found to be doubly refracted. It is converted into two rays. One is fast ray, the other is slow ray, or one is ordinary ray, and the other is extraordinary ray in case of uniaxial crystals. O ray always vibrates in the basal plane, and E ray always vibrates in the plane that contains the incident ray and the optic axis or the C axis. And the velocity of E ray is found to vary, because of which it describes an ellipse. Its wavefront describes an ellipse. But O ray, because its velocity is constant, as it vibrates in the basal plane only, and its velocity is found to be uniform, a constant velocity throughout the crystal, and its velocity matches with that of the E ray along the optic axis direction. That's why along optic axis direction we find that O ray and E ray, they match if they see the C axis direction. So there they match. You see the circle describing the wave surface of the O ray. This is the ellipse describing wave surface of the E ray. This is E ray wave surface. This is O ray wave surface. So they match along the C axis direction. So because it is circle, its velocity is constant. This ellipse, E ray, its velocity is matching with O ray along C axis direction, and it is found to be different in different directions. So it is ellipse. Based upon this character, the uniaxial crystals are described as positive or negative depending upon the velocities. If O ray has greater velocity than E ray, the mineral is said to be uniaxial positive. This is the case of uniaxial minerals. If O ray has velocity less than E ray, it is called uniaxial negative. So this is based upon the velocity, and the phenomenon of getting two refracted rays from a single incident ray is described as double refraction, and this is a phenomenon which is related to the internal atomic structure of the mineral concerned. So I discussed what is double refraction, how it takes place in minerals, and how calcite is the mineral that displays well the phenomenon of double refraction. And actually, if you take into account the calcite crystal and imagine the image produced by a dot over it, and we see the two images. One is ordinary, the other is extraordinary. One obeys the rules of refraction, the other doesn't obey. And I discussed that these two rays, they vibrate on two mutually perpendicular planes. How can we identify it? How can I establish it? To establish it, we use another mineral, which is tourmaline. Tourmaline is a mineral which has the property to absorb light in one of its vibration direction and allow the other set of light to pass through. If we place such a tourmaline plate over it and rotate it over it, we will see that one of the image, these two images will vanish, the other will appear. Next, if it is rotated 90 degree, the other image will appear, the next image will vanish. That means these two rays, they vibrate in two mutually perpendicular planes. It can be well studied by putting calcite experiment and over this calcite by using the tourmaline plate, because tourmaline has the property to absorb naturally in its atomic structure one of these two rays in one of its direction. So once that direction is detected, from that direction, if we rotate 90 degree, other ray will vanish, and the first ray which was vanished in the first phase, that will appear. Again rotate 90 degree, same thing will repeat. So in 90 degree rotation, one will vanish, the other will appear. Again 90 degree rotation, the other will appear, the first one will vanish. So that clearly proves that these two rays, they vibrate in two mutually perpendicular planes. So this phenomenon of getting two refracted rays from a single incinerator is double refraction. I think this is clear to you all. Thank you for giving a patient hearing to this talk.